and introduce today's speaker. Susan Knack-Brown, principal at Simpson, Gumpertz & Hager, has been with SDH for about 13 years and has worked on a range of building enclosure investigations and designs involving both contemporary structures, such as the Fisher Center for Performing Arts at Bard College, and historic landmarks, such as Boston's Quincy Market. Susan specializes in large-scale preservation projects where she applies emerging technologies to restoring landmark buildings. Some of Susan's signature projects include the multi-phase, multi-year roof rehabilitation and skylight restoration on the New York State Capitol and the roof replacement on the Massachusetts State House. She has also worked with the First Church of Christ Scientists to assist them with condition assessments, interim repairs, long-range strategic planning, and restoration designs for the Plaza and 5 buildings on their Boston campus. Without further ado, I'm now going to hand over the mic to Susan, and she will begin her presentation.
Thank you, John. Hello, everyone. As John mentioned, I work in our building technology department, specializing in building enclosures, and so we get into a lot of the energy usage issues that I want to talk to you about today. I am from our Boston office, and the examples are primarily East Coast for that reason, but I assure you a lot of the conclusions still hold true to the West Coast in California. So the learning objectives, they're the same as were published in the advertisement. Generally what we're trying to do is help you today understand some of where building energy usage is occurring and how you can make improvements that are both a range of simple interventions and more extensive interventions, and start to think about what the payback would be on those changes and what that might mean to the building performance. So let me start by just laying out why would you want to make improvements. There's a couple of questions I had Jonathan put together just to gauge what people know about how much energy we consume in our buildings to date. So if you can each just answer those quickly, it'll give us an idea of where do you think we put energy usage. So it looks like maybe most everybody has answered. And as we start to get through into the presentation slides, we'll see what the exact responses are to these. The three questions being, what percentage of energy is consumed in the U.S. for buildings? What does that mean in terms of the global energy usage? And then, what is the biggest consumer of energy usage in commercial buildings, which is what I'm going to focus on today. So switching back to the slides. So just a little historical context first in terms of our energy usage as a nation. This is looking at energy consumption for the United States. This is all of our energy consumption, and you can see obviously we are still trending upwards. In the last couple of decades, there's been some downturns in different types of energy usage or different sources, but generally as a nation, we're still consuming more energy. And this is going to be the case even as we get more efficient because our population is still growing. The next slide is showing you just a projection that's available through the U.S. Department of Energy on what the building sector is going to use. And they predicted a small downturn still after the 2008 recession just because building projects started to decline and we had less usage, but that shortly by next year, they were predicting, several years ago even, that we would continue to rise in terms of energy consumption used by buildings, even as we get more efficient, just because we're putting more square footage. Obviously, the distribution of what we're using as energy is changing, and then there's a small rise in renewable sources as some of our energy consumption. So back to the first question I just asked you. In terms of the breakdown, the United States uses about 19% of the global energy in the world. We were just passed by China in the last couple of years. Of that, 41% of that is our building structures. Combined residential and commercial buildings are higher than any other source. It's higher than our cars. It's higher than our industrial and manufacturing goods. And that equates to approximately 7% of the global usage in the world is related to our U.S. building sectors. So we certainly have a lot of energy usage that comes from our buildings, and there's a drive to make it more efficient for that reason. Just as a sort of stepping back a little bit, when we think about what we use in energy efficiency, some of this has to do with the end building and how it operates. Some of it has to do with the infrastructure and how we get energy. Two primary sources in what we use as a building is natural gas and electricity. But what that means in terms of efficiency is quite different. Natural gas, there's very small extraction or piping losses. So if you had 100,000 BTUs extracted from the ground, there's only a 5% loss, and that can generate about 95,000 BTUs in the actual building. When you're looking at electricity, there's a huge drop in terms of efficiency. There's about 70% loss to generation and transmission losses. And so that obviously equates into a much less efficient source of energy. That also means there's a difference in price in terms of payback. Now, the exact price difference per therm really depends on where you are in the nation, but just looking at this, you get some sense of the disparity between what it costs per therm if you're using electricity or natural gas. And some of that comes into play when you get into mechanical systems especially. But it also, you can understand why lighting and other things may give you pretty good payback just because electricity is so inefficient. This is just another chart looking at the same U.S. energy consumption breakdown of inputs and how we are using that energy. We take a closer look at the output. That's again showing up what we saw in that previous graph, that residential and commercial combined as buildings is about 40 to 41% of our energy usage. Now 54% of that is residential and 46% of that usage is commercial. So commercial, it has a smaller percentage than residential, but you can see that imagine that it's an easier impact for a lot of us in making improvements to look at commercial buildings, and that's what we're going to focus on today. Industrial process is about 32%, transportation about 28%. So how do we use that energy? I saw a bunch of different answers in terms of how you answered questions earlier. And combined for residential and commercial, the largest usage related to buildings is in space heating, followed by water heating, space cooling, and lighting. That breakdown doesn't hold true, though, when you look at just the commercial sector. In the commercial sector, which this chart is showing you, and it's a little small, hopefully you can see it. In the commercial sector, lighting is actually the highest usage of energy. And you can imagine why that would be the case. Lights are on continuously in offices for 12 hours a day. You don't have water heating and some of the other energy uses that you'd have in residential. They tend to be larger floor spaces so that you have less envelope per volume, so less energy lossage through your exterior envelope. So obviously there's a great deal of energy usage that happens with buildings. Some of it's related to lighting and mechanicals, and then some of it's related to the building envelope. All of the efficiency of this is really tied quite a bit to the age of the building and the age of the systems that you're dealing with. And this graph is just showing you a breakdown in terms of the age of a building stock. You can see that from a square footage space, obviously we're tending to increase with each decade the amount of square footage we're doing, but there's still a high percentage of square footage that is reasonably old. Let me go back, sorry about that. in looking at this graph, about 54% of the building stock is pre-1980. And when we look later at some of the energy guidelines that we think about, a lot of our modern performance standards didn't start to come about until after 1980. So you can see that a large percentage of the buildings probably weren't constructed with energy usage in mind. Hopefully that's laid out the case as to why energy usage is important and why buildings especially we need to concentrate on. I wanted to next go and spend a little bit of time just giving you some retrofit basics, starting with looking at what is probably one of the most sort of high-profile case studies in terms of historic building of late, and that's the Empire State Building. Full disclosure, SGH was not involved in this project, but it's made a lot of headlines, so I wanted to briefly touch on it. Their retrofit of this building was completed in 2009, so we have almost 5 years of data on the performance. And generally, they've been able to get 38% reduction in their energy usage since they completed the retrofit. And this was actually an interesting case study. There's some performance tiebacks based on what was incentives based on what they were getting for energy returns for the designers and those involved in the project. Now, the entire project cost $550 million, and it focused on a number of different areas, of which only a few were the building envelope. They refurbished windows, which is a building envelope upgrade, but the rest of them are primarily related to electrical or mechanical systems, replacing chiller plants, installing insulation behind radiators, looking at new controls and metering, trying to look at energy management systems, upgrading the elevators, and dealing with the lighting. And from that alone, they're getting a 40% reduction in how that building operates. So that's a pretty successful project, and I think we all would be quite happy if we got a 40% reduction in our energy performance. So how do we go about doing that? I sort of have defined this into a 4-step process. The first being a building audit or benchmark. And by that I mean, know what your existing building is. What are your existing systems? How are they constructed? Are they operating efficiently? Do you have user comfort issues? Is there complaints? Is there other maintenance or operational issues that might be come into play as you make decisions on what you want to tackle? The second step is setting goals and parameters. No project is going to be successful unless everyone is upfront in the beginning of what they want to accomplish with the project, what they have for budget and funding to do that, how much disruption they can handle, and other outside factors that might come into play. I've dealt with clients who have the goal of a net zero building, but most clients are looking for energy improvements and things like return on investment, and they might not have other incentives. So knowing that up front really comes into play as to how you want to tackle the project. The next step is analysis, looking at energy models, life cycle analysis, return on investment. All of these steps we'll talk about a little bit more as we get later into the presentation. And then the final step is actual implementation, to which I'll present some case studies as we get farther along. So looking a little bit more at building audits and benchmarks. As I mentioned, you really want to know how your building operates and how it's constructed. So is there user comfort issues? How does your building envelope perform? Are there leaks? Are there air leakage and drafts that people are complaining about? Is there other deterioration that you want to address as part of comprehensive upgrades to the envelope? They might even be driving why you're making improvements to the envelope, and then you're just making energy improvements as an add to that. Does the building envelope have an air barrier? What is the thermal performance of the building envelope? Is there windows? Are they single glazed? Are they IGUs? What is the surrounding materials? What's the wall insulation? What's the roof installation? Are you getting solar gain through the envelopes? People on the south side of the building are complaining about it being too hot, while people on the north side are too cold. Then you also have to look at your mechanical system. How is it being maintained and operated? Does it have setbacks? What's the age of the system? How efficiency? What its fuel sources are? What are the control systems? Does it have economizers What is your intake air versus, recycled air? What do you actually need for ventilation? And then lighting, is there occupancy sensors? Do you have high efficiency fixtures? Is there opportunities to use natural light instead of artificial lighting and potentially limit your lighting load that way? In this presentation, we're going to spend probably a bit more time talking about user comfort issues and building envelope performance issues. And I want to spend a little bit more time right now just giving some background in case some of this terminology is not common to everybody. So looking at a building envelope evolution, and I think there's a couple of questions associated with this one too. So one of the questions is, what decade saw the rise of the use of weather barriers? If you remember going back, most of our buildings were constructed pre-1980s. And then what do we know about what are the weather barriers or the barriers that are part of a wall performance? So I think we may have most votes in place. Generally, it looks like there's consensus that weather barriers probably came into construction in about the 1950s, and that generally rain screens aren't part of the wall's performance. So let's go back to the presentation and take a closer look. So this is a really 40,000-foot simplification of the evolution of building enclosures. But generally over time, it's only in the last 100 years that we've seen real changes in how we construct buildings. Residentially, it's a lot of masonry and wood. In commercially, even, it's a lot of load-bearing masonry. Then we evolve into sort of transitional masonry, where we get the idea of steel or concrete frames, often still with mass masonry walls. And then finally we get in the 1940s onward, 1950s, into contemporary walls, where we're starting to get veneer walls, curtain walls, and what we think more is in terms of modern buildings. Looking at a timeline for contemporary enclosure construction, it's about the 1930s that we start to get the idea of a weather barrier, that there needed to be a barrier within the wall system to control water entry into it. So 1930s, there's a study published by the University of Minnesota that recommends basically a building paper or felt within the wall system to help control weather. 1940s, you get some expanded use of those weather barriers and vapor retarders. So that evolution came out a little bit earlier than you guys may have thought. But it isn't until the 1970s that we start to really see insulation. That first energy crisis pushed insulation usage in buildings. And it isn't until the 1980s when the National Building Code of Canada started to really get concepts of wind, water, and vapor protection and the idea of a comprehensive system and flashing. They then revised that building code in the 1990s to first start looking at air barriers and air permeance requirements. And it isn't really into the 2000s that we start thinking about whole building energy requirements. So a lot of the concepts that are part of a more modern building enclosure didn't come out for that first 54% of our building stock. And that obviously has an impact on how those buildings are performing. So we define there to be 4 barriers for modern contemporary wall performance. The weather barrier, waterproofing, which is going to control groundwater and rainwater. And then an air barrier, vapor retarder, and insulation. And those are really more for condensation control and energy consumption. Just spending a little bit more time talking about them, Weatherproofing obviously has less of an impact in terms of your energy consumption, but if you start to think about sustainability and long-term durability of building components, having waterproofing, having flashings, and some way to control water entry into the wall system will really expand the durability of those products, let you maintain them longer. You're taking advantage of the embedded energy that is already there if you can maintain your building system. And obviously, we're talking about this in the context of preservation. And waterproofing is important in terms of keeping the buildings functional and having long lifespan. In modern walls, there's typically two types of walls. You can get drainage walls, which have a facade and then backup waterproofing with flashing, the idea of redundancy. Or you might have in modern walls the concept of a barrier wall system where you have like precast concrete that has seals and relies on a continuous surface seal for its waterproofing. This is more close to what you would think of in terms of historic buildings where you have a mass masonry wall and you're relying on that wall thickness to be the water screen. It'll absorb some water, but it'll evaporate out over time. Vapor barriers, in case you're not familiar with the concept, it's the idea of controlling moisture flow through the wall system. Typically, moisture flows from a warm, high vapor content area to a cold, low vapor content. These diagrams are drawn with the design of being in a northeast climate where you would potentially get vapor flowing from the inside in like a museum space that's humidified, and without a vapor retarder it could condense on a cold exterior sheathing. You might have in hot, humid climates the reverse where you've got exterior warm air traveling to the interior and potentially condensing within the system. Including a vapor retarder on the warm side helps to limit that moisture from flowing through and getting condensation within the system. Air barriers are probably more important in terms of your climates in California where without humidification you don't have as much of a warm, hot climate. Here, air barriers are important for two things. There's a big part of energy control, and that if you don't have a continuous air barrier, you can get your humidified and conditioned, or your conditioned air that's on the interior of your building, whether it's cooled air or warmed air, traveling through the envelope and escaping out. And this is a high source of energy loss through a wall system. It's also potentially, if you're in a cold climate, you can get condensation within the wall system if you have improper air barriers or don't have an air barrier. Having a continuous air barrier prevents that airflow through. It means you have a more efficient building and you can better control your interior conditions. So just comparing systems real quickly with those four barriers in mind. Historic mass masonry buildings don't have a dedicated weather-resistive barrier as we talked about it. Instead, they're sort of a mass masonry. They absorb water, and then typically they work by evaporating water to both the interior and exterior. And the way they function is that you don't absorb enough water that it leaks through to the interior. Contemporary walls obviously have weather-resistive barriers either from a surface seal or from a drainage system. In terms of a thermal performance comparison, historic mass masonry walls, you get about 0.2 R per inch. So a 12-inch thick wall, which is not a very thick wall, is only R 2.4 in terms of energy and conduction through the wall system. In comparison, for the contemporary barrier walls and the contemporary drainage walls, I'm listing what are a range of code requirements from California. California, obviously, if you've ever looked at the energy code there, is complicated in that you have so many climate zones and different requirements within the state itself. But there's basically a requirement of ranging from R25 to R3.7 for mass, light, or heavy masonry walls, and approximately between R16 and R10.2 for metal frames in terms of comparison for a contemporary drainage wall. And those R values are approximate. The code actually lists U values, and the R value is approximately inverse of the U value. In terms of that air barrier function, comparing a historic building to modern buildings, mass masonry walls are actually poor air barriers, and you don't get a lot of performance out of that wall system. And then in contemporary walls, there's typically a requirement that you have an air barrier. California only requires it in your climate zones 10 through 16, so not in all climate zones. The more mild ones, it becomes less of a concern. Here in Massachusetts, you have to have a continuous air barrier on all new buildings. And then vapor retarder requirements really vary depending on the climate zone. A historic mass masonry building doesn't have any vapor retarder within it. Just as a rule of thumb for you, I've listed some modern materials and giving you an idea of their R value per inch. So wood itself, if you just had a wood sheath building, for every inch of wood thickness, you've got about an R value of 1. Compare that to closed cell spray foam, a very modern material, you have about 6.4 R per inch. And everything else ranges in between. So that hopefully gives you a little bit of background on modern performances and how buildings have evolved. Let me talk a little bit more about the third step in my outline 4-step, and that's looking at the analysis and whether, what will you get out of your building and starting to plan ahead for some of the intervention. And what I have pictured here is an energy model from an investigation that we did on a modern building, but it was a building constructed where they had real concerns about heat gain and user discomfort, and we're trying to look at ways to improve that. So I don't know everyone's familiarity with an energy model, so I just want to spend a little bit of time talking about what is an energy model. It's basically a virtual replica of the building that you're going to input a bunch of design parameters, and from that be able to calculate, on an annual basis, some real data that inputs in real weather data from your surrounding atmosphere or surrounding area. You can pick your region. Energy modeling is a tool. Like all software tools, it's only as good as the user is. And that a lot of the interface is fairly easy to do, but that doesn't necessarily mean that someone who's inputting that understands the science behind the calculation engine. And as a result, you can get significant errors. So tools are tools, and you need to understand the limits of that. The graphics that are included here is some 2D modeling, 2D thermal modeling that we've done in a case where we had an existing building looking at a window within that building. And the modeling shows where you're getting conductive heat loss through that. So if you just take the U value that's published for a replacement window and put it in your wall system and assume that is the U value that you have in situ, that's not what you'd actually have, because you're getting conductive heat loss from its contact with the surrounding construction. And that's the sort of input parameter that the user really needs to know what they're putting in and what the data represents. So how do you create an energy model? You start with the building location and geometry, and then you break it into the thermal zones. This is a floor plan of St. Paul's School, which is a case study that we'll talk about a little bit more later in implementation. It's just showing you the layout that we have. This shows you how we defined it for the sake of our energy model, broken into different thermal zones and blocks for our analysis. Our next step is to put all of those inputs in. So putting in the characteristics of the building envelope, the walls, penetrations, roofs, floors, and really understanding what the in situ performance is, not just what published data would tell you that the wall is. And that often requires some additional modeling beforehand, doing thermal components to understand that. You also have to put information in about the internal components of the building itself, partition walls, contents, where you've got openings, potential airflow between different thermal zones, that sort of information. You're going to put in inputs about the internal loads and schedules. How many occupants are there? What is the lighting? What equipment? What is the heating parameters? What is your setback temperature? What is your heating temperature, cooling temperatures? There's a number of variables that have to get put in, and you can tell from the input sheet there just how many there are. You'll also have to put in information about the HVAC system. What do you have for natural versus mechanical ventilation, what type of system, how many zones are there on the mechanical. From that, you'll get a number of outputs: the annual and peak energy usage, the annual and peak energy cost, based on some different schedules, energy that you've defined or surfaces, internal load components, and interior conditions. So what good is an energy model? There's a number of different applications for energy modeling. LEED compliance, building code compliance, and we'll talk about both of those a little bit more. Forensic and troubleshooting, like that example I showed at the beginning of the presentation, where occupants were unhappy with the current performance of it. In new construction or renovation, these energy models will help you define your HVAC equipment sizing. So how much cooling do you need? How much heating do you need? It'll help with questions of envelope and system optimization. It'll help you do some parametric analysis, looking at different options, and then economic analysis, looking at the payback on those various options. So I mentioned LEED compliance. At a minimum, to get LEED compliance now, you're going to have to show a 10% improvement over the baseline performance. And then to get, and that's for new buildings, with slightly different requirements for existing. And you have to show that the baseline building meets ASHRAE 90.1 or the California Energy Code. To get additional points under LEED compliance, you have to then prove further reductions in the energy usage. And this table just gives you a highlight of points to this. Now this, what I'm quoting here is LEED 2009. Just for full disclosure, LEED version 4 is now out. There's small changes in exactly what those requirements mean, but the general workflow requirement is still the same. And so you really have to plan on doing energy modeling if you're going to get into LEED. Under the energy code, you can also get into compliance. Here I'm referencing the IECC, so the International Building Code version, which is applied to many states with small modifications. California, of course, has its own requirements, but they're based on some of the similar parameters, and they have their own software tool for that. But you get into some of the code required compliances if you exceed maximum glazing allowances, or that you have to prove out that you're, because you want to do something that's atypical in addition to existing buildings or in other areas to show compliance with the code. So how can an energy model actually save you energy? New construction, you can sort of obviously see the parametric analysis will help you to fine-tune the building. How are you going to orient it, versus sunlight, solar heat gain, what's its building shape, shading elements. It'll allow you to look at optimizing insulation thickness, your glazing, your HVAC system, etc. Under existing buildings, it still can help you save energy. It lets you do energy auditing and retro commissioning, and it lets you evaluate the capital improvement projects that you want to tackle. Obviously, because we're talking about historic buildings, we're going to focus on existing buildings. I have just sort of 3 simple case studies here to try to highlight what you might get out of energy modeling. The first is a real basic box that we just used as a way to highlight what you might see in terms of making energy improvements or insulation improvements to the building envelope. So we assume that this is just a mass masonry building. For the sake of this discussion, we modeled it in New York City. It had about 20% glazing, just assuming steel frame Hope windows. We assumed it was an uninsulated roof and exterior walls, and that it was generally going to be converted from a more industrial application to an office occupancy. And we modeled a bunch of different scenarios just to look at what you were getting in terms of payback on money spent for this hypothetical case. So on the far left, we have a scenario that is the existing building. And we're looking at an annual expenditure for its energy usage, assuming that there's no wall insulation, but you've got the original steel windows, no roof insulation. And you can see you have pretty high total energy cost, and that's including cooling and heating. We then looked at a bunch of different scenarios. First, assuming that you wouldn't put any wall insulation on and you would just look at making improvements to the roof and windows. And that we looked at scenarios where we made it compliant with ASHRAE 90.1. So the first scenario, we're keeping the original windows, just changing out the roof insulation as part of a roof maintenance replacement, and looking at putting enough insulation in to meet 90.1. And you can see you get a reduction in the total energy. We then went a step farther and said, well, what if you were to change the windows out to make them windows that were compliant to 90.1? And you can see that there's a further reduction. And we've done nothing with the walls from there. We then looked at the scenario of, could you go above and beyond? Could you pay for the really expensive high-end, triple gaze windows, put twice the insulation on the roofs? And what would be, your energy savings if you went to that scenario? And you can see there isn't actually a large reduction from the previous one of just meeting 90.1 for the roof and windows. We then repeated this exercise, assuming that we started to actually tackle putting insulation within the walls. So the middle purple box are scenarios where the roof and windows are compliant to 90.1, and we've put in half the insulation required for the walls. And you see you get a further reduction, but then going above and beyond with extra special windows and increased roof insulation doesn't really give you payback. Then we go to putting full wall insulation in, and you see that it's an even smaller drop when in those same scenarios in terms of energy savings. So just adding half the insulation made quite a bit of difference. And then going to 2 times the insulation really didn't change the total energy usage. And so just having this kind of information helps you have an informed discussion about where you might get payback on the improvements that you're making. And something that, for the sake of this comparison, we took the theoretical cost for insulating the walls. So, that energy reduction that you were getting from going from just dealing with the windows and the roof to something that might be more invasive. We assumed here that you'd be demolishing plaster on wood lath, putting in closed cell foam stud walls on the back side of these mass masonry walls, and putting up painted gypboard. And for the building area, we just made in this, a rough calculation using means and came up with that it cost about $280,000. But the payback that we had per year was only $8,300. So not accounting for net present value of money or inflation, that's 34 years to pay back that, which is a pretty invasive requirement. So this is the kind of analysis that some energy modeling can tell you. Just another case study real quick. This is a private residence in the Northeast that we were asked to look at. And we were asked to look at what would be the returns on adding extra insulation to the walls and roofs. So that you're going to increase the wall and roof by 50%, but that only resulted in a 15% reduction in annual heating energy costs. And it resulted in 15% reduction in peak load. The third case study is something similar. We're looking at a museum project here and comparing a baseline to the possible improvements of adding 4 inches of closed cell spray foam or just changing out all the lighting to be LED lights. Under this, and you're comparing it to the baseline, adding the insulation gave you a 5.8% return compared to baseline, but changing into LED lights gave you almost a 26% increase. You may be looking at the numbers and noting that changing to the LED lights increased your heating costs, but lowered your cooling costs compared to the baseline model. And if you think about that, our lighting actually adds a fair amount of heat and helps us heat our buildings in the winter, so that having LED lights, which are cooler, would require you to spend more on heating but less on cooling later on. So the conclusion, obviously, in this case is lighting has a much higher impact compared to the building envelope modification. So is that always the truth? Just some concluding marks in terms of the building envelope modification impact. You really should look at it part of a parametric analysis. They do have impact. I mean, adding insulation still gave you a 6% reduction in that last model. But there are diminishing returns if you have a pretty airtight building that has decent insulation levels. Going above and beyond to add extra insulation is probably not going to be worth the cost if you have a building that is reasonably functioning to begin with. And that mechanical systems, lighting, and plug loads have a much bigger impact on building energy usage. So let's move on to some implementation case studies. Going back to the Empire State Building briefly, and just to reiterate the point that we sort of were talking about at the end with the building modeling, the energy modeling. Most of what they did on this building was related to mechanical systems and lighting. It wasn't extensive building envelope retrofit. And so I just, a lot of your highest potential, whether you're dealing with, with historic buildings, modern buildings, is dealing with the HVAC, lighting, and office equipment. And that's probably, often your lowest hanging fruit. As you can replace out lighting with high efficiency fixtures. Think about office equipment, nightly shutdowns, so that computers aren't running out all night. Where you can, shutting equipment down, making upgrades. The HVAC, do maintenance. Make sure that what you have in your existing systems are running optimally. Change filters. Do retro commissioning to make sure that you're getting the performance expectations that you want. Think about setbacks as you can, so that you're not heating and cooling when the building isn't occupied. Install economizers, replace inefficient equipment. These are really going to be paybacks, whether it's a historic building or whether it's a modern building. And it's worth going back and looking at the data that you have. I heard a story recently from a modern building that was supposed to be incredibly energy efficient, and they were not getting the performance expectations they were, but they were looking at the data and they tried to figure out what the anomalies were. And what they then quickly went out in the field and looked at offices on the south-facing sides and realized because of design issues, the HVAC systems weren't running in individual offices when there wasn't occupancy. The HVAC systems actually had occupancy sensors. But on the south-facing side of the building, that caused offices to heat up when people weren't in them, and occupants didn't like the coming back to an office after they'd been in a meeting for several hours and having it be warm. So they quickly put crepe paper hanging from the exhaust systems, and overrode the motion sensors so that the AC systems were running 24 hours a day. This sort of retro commissioning would allow, somebody went back, they took that out, they changed the frequency with which, occupancy sensors turned off and on the equipment, and found a compromise that had both, user comfort and gave them an efficiently operating building. If you've gone through and looked at the lighting, looked at the mechanicals, hit some of the other low-lying fruit, then you may want to start looking at enclosure improvement strategies. And there's some low-hanging fruit within enclosure improvements as well. Again, it's maintenance and glazing improvements. So, making sure that you have seals in place, the gaskets around doors and windows, penetrations through the wall system are sealed. Glazing improvements, you can look at films or shades to control heat loss or heat gain through windows. Beyond those low-hanging fruit, there's more moderate changes to consider. So that's, refurbishment or component replacement. So you can imagine windows and IGUs are a somewhat invasive but more moderate change to the building enclosure. More substantial changes would be things like, overcladding, recladding, or putting insulation inside on the interior of your building. For the sake of the remaining examples, I'm going to focus more on the moderate changes and substantial changes and what some case studies might look like with these. I'm not going to talk at all about overcladding or recladding. This is a preservation talk, so I'm assuming that we cannot make substantial changes to the building exterior, so I'm not going to present those case studies. Whatever you do, you want to verify the improvements. And there's a bunch of different tools that you can use to do that. Water testing, IR cameras, air leakage testing, energy modeling, both before and after with input data, and commissioning of the repairs you've made just to make sure you're getting what you expected out of the system. So before I get into a couple of case studies, I just wanted to sort of think about what the balance is. Making enclosure improvements, especially more moderate or substantial ones, are going to provide you, opportunities to make bigger improvements that might not be just energy related. It'll allow you to address any other enclosure issues. So these type of interventions might be appropriate if you have leakage or other deterioration that you have to address anyways with your building enclosure. If you're already going to be doing a gut rehab because there's a change in use or interior conditions, that might trigger a reason to go and make enclosure improvements. You'll have an opportunity to have improved user comfort. Something that you should always do is, if you're going to make these changes, coordinate them when you're changing out HVAC equipment so that you can get the properly sized equipment for what you expect your building enclosure to operate at. And all this is going to help you reduce operating costs. But there's certainly, downsides to these more invasive, even, moderate or substantial. You really have to look at payback. As I've mentioned in those energy case study models, it's not always an immediate payback on some of these, and that shouldn't just be your motivating driver. I just popped up 2 pictures of a project that we're involved in, a bus maintenance facility, not a fancy structure, where they wanted to go and put photovoltaic panels on the structure, and they actually put enough panels on to completely supplement their energy usage within the building. All their electricity they generated enough electricity to cover all of their electricity needs. But in doing this project, they assumed they could just put the panels on the building, and that wasn't really the case. Panels were heavy enough compared to a lightweight structure. They had to make structural modifications. They had to change the roof system out. And payback wasn't within the lifespan of the photovoltaic units, except that they had a federal grant to do it. So a lot of these projects don't have payback. There's a lot of disruption when you get into these types of projects, and you have to look at tenant disruptions, potential loss of income to implement this. There's always a question of what's sustainable. If you end up tearing off products or replacing out existing windows, you have to think about the embedded energy within those materials, and how does that compare to what you're getting for energy improvements. And just a loss of historic material as well. So some window strategies. There's 5 factors that you need to think about when you look at window energy performance. Conduction, so how much heat you're conducting through the window. Solar radiation, how much heat you're gaining or losing through the window due to the radiation. So a low solar heat gain means you have less solar heat transmission, better shading. You get a reduction in cooling loads. High solar heat gain coefficient means in a winter climate you get more heating through the windows that'll help your wintertime heating. How much air leakage you have through for that energy loss. How much visible light you get through that might supplement your need for artificial lighting, and what the light to solar gain coefficient is. So, the more visible light you let through often means that you get higher solar heat gain through that, so it's looking at the balance between those 2 factors. Just a little bit more on air leakage through the windows. There's a lot of words on this. In general, air leakage through a window is a significant contributor to energy costs. It's also a significant contributor to user comfort issues. Generally, operable windows are worse than fixed windows. The larger a window is, more glass area per perimeter and sash perimeter and window frame perimeter, the better performance you get because it's the perimeter conditions that really are associated with air leakage. And so your fixed windows tend to be your best windows. In terms of replacement windows, putting a modern window in might give you opportunities to get thermally broken frames, insulating glass units with tints, films, low-E coatings, argon-filled spacer areas. to change operability so that you can get improved operability. For instance, a casement window has better air infiltration performance than a slider. And so, you've got a potential improvement there. And then, there's an idea of locating it with it aligning with your insulation and that you'll get better performance. So these are some potential benefits of replacement windows, but it doesn't always pay out that replacement windows are better. And I'll show you a case study where that didn't prove to be true. Just as an aside, this is a picture of a real high-end replacement window. Dual thermal breaks, triple pane glazing, the best you can get in terms of a current modern window performance. This is a 2D thermal model of that window, looking at interior temperatures, assuming that it's all on its own, not within a wall system. And you can see you're at about 58 to 59 degrees interior surface temperatures in this model. You place that window in a wall system, properly aligned in a modern wall system where I'm showing here, so that this window aligns with insulation. So the thermal breaks and the insulation all align as I'm showing. You get a performance that still drops about 10 degrees from its theoretical window performance, but you've got between 49 and 51. You put that same window improperly aligned so that the thermal breaks don't align with the insulation, or in analogous to what we're talking about, you would put this high-end window in a mass masonry historic building, you don't get anywhere near the good as same performance. So all of a sudden now, our thermal breaks are not aligning with our window insulation. You've got a conduction loop between the window frame on the interior and the cold exterior masonry, and you've dropped another 10 degrees in performance. Moving this example of sort of modern into a historic building, this is a building that we ended up being involved in, this sketch that was a 1930s mass masonry building where they were doing a gut rehab of the interior, putting insulation in, replacing out the windows. But because of historic reasons, they didn't have any flexibility in placing the window in position within the wall, so that the window was placed in position with the cold exterior masonry. So the published data from the window manufacturer indicated that the window we were buying, which were aluminum casement windows, thermally broken. They were paying for the stainless steel spacers, the argon in the insulating glass, low E coating, was a theoretically 0.44 U factor. When we modeled this system in its in situ conditions, we ended up with a 0.707. So not quite double what the U value was theoretically, but quite a bit of reduction in performance because of where it aligned. And this is the kind of input that we gave to the HVAC consultant so that he could properly size it in his energy model and size his equipment. So the first case study example I wanted to talk about is a window replacement project. This project took place at St. Paul School, which is in New Hampshire. It's a building that was built in 1936, uninsulated masonry walls and steel frame windows, single light, single glass pane windows, fixed and operable. The building is used as classroom and office space. So we were initially called out because the building wasn't performing well. There was a lot of complaints about thermal discomfort for the occupants. They felt that it was cold and drafty. They were putting plastic up over windows. And the building had a really high energy usage. They tried to put setbacks in to do some of those low-hanging fruit in terms of their energy performance. But they found if they set the temperature back at night or on weekends, they couldn't raise it in time on Monday morning after a weekend of being cold that the room was warm enough because for the classes, just because there was such a slow response to the system and there was such poor thermal performance of the exterior. So we came out and did some initial field air leakage testing through this, both qualitative and quantitative. And we found that air leaked through the caming joints around the operable sash and through the joint between the window frame and the stone. So our initial testing found that we had an air leakage rate between 0.748 to 2.93. That's 2.5 to 10 times the industry standard and about the same amount from what we ended up with replacement windows later on. So they were very poor performing windows in terms of air leakage. And looking at them, you quickly could see why. There was no gaskets or seals on the system. They were just metal-to-metal connections. And around the perimeter of the window, they had poor window perimeter seals, and you had air leakage through the came joints. John, is it possible to bring that video up? So what I have here is just a quick video. This is a qualitative air leakage test. So we end up pressurizing a chamber on the inside and using theatrical smoke, and it blows through the window. So what you are looking at there is smoke coming through from the interior to the exterior because of air leakage through those window systems. So it's just a real qualitative way to get an idea of how bad the air leakage performance was. So once we had this basic idea of this poor performance, St. Paul Schools asked us to start doing some energy modeling and that parametric study and trying to look at what they could do for improvements. They clearly wanted to replace the windows, but they also were starting to think about could they look at insulating. They determined pretty quickly that that was too costly and disruptive, but it was an option that they considered. They also wanted this model to really start to look at, what were the potential savings if they improved the windows. Now, we had a really unique opportunity. So we did our initial energy model, which I showed you there, but we also had, because of some partnering opportunities, a chance to study and do a little bit of research on this one. Through some grants and our own internal initiative, we partnered with the school and with Honeywell, and we actually collected data on the energy usage and weather data, temperature data, both before and after the window replacement study. And we used that to validate our energy model, and then as a way to go and see what improvements we were getting and whether they were really getting the energy performance. Honeywell provided some sub-metering data for us, and the St. Paul School IT department actually put up a dedicated IP address so that we could remote live access and get recorded data between our offices and their school. The other step that we did as part of this is we went back and did a whole building air leakage, not just the initial air leakage that we did through the windows. So we pressurized the entire building and use that data both before and after to really calibrate our model based on some general assumptions that are typically used in energy models and actual field performance of the air leakage. So what we found in terms of the impact we got back, I told you before that just replacing the windows and air leakage through the windows, we had a 2 to 10 times better performance. What that means in terms of the entire building air leakage is pre-windows, it was 0.89 CFM per foot squared. After, it was 0.63 CFM per foot squared. That works out to about a 30% improvement in the entire building air leakage by replacing the windows. So this is just some pictures showing you the window installation, which occurred in the summer of 2012. All of the windows were replaced with new steel frame windows with IGUs. And then if we go back and just from that qualitative performance and how we did 2 videos, so just a reminder, first video is what the preconditions looked like with smoke filtering through the air pretty rapidly. And then the second video that we're just bringing up shows the same test run, same windows, after the window replacement. And you'll note there's no smoke coming through. Obviously, our testing proved that out as well, just in terms of air leakage rates. But this is just a quick example showing what you can get for improvements between that. In terms of other reductions, so replacing the windows out resulted in a 10% reduction in their energy usage for the building. More importantly than part of what made that feasible is that replacing the windows out allowed them to implement setback temperatures. They could actually bring temperatures up in classrooms effectively at the beginning of the day now, and that would allow them to turn lower temperatures at night and on weekends. The other thing that all of our analysis sort of proved out is we did a comparison because we were able to better calibrate our model using the whole building air leakage testing, that if we hadn't calibrated it, the model predicted 65% higher heating loads requirements than the calibrated model with the whole building air leakage test. So this case study really gave us a chance to prove that the more information you can put into your energy model, the better your results are and the more fine-tuned
Did you take off the tape? No.
predictions to be. And that we expect that next time they change out their heating systems, that they'll be able to get even better energy performance because they can size the system better to what they now have. So that's the first case study on looking at windows. The second case study I wanted to talk about is one where we were actually involved at looking at window replacement versus restoration. It was a project where we did mock-ups of both. We were partnered with an architect. This case study is actually published in an APT bulletin if you want to know more about it after this presentation. So the building is the Lafayette Building in Washington, D.C. It was constructed in the 1940s. It's a National Historic Landmark, and it was undergoing a comprehensive building renovation. So exterior facade, interior restorations, new MEPs, security upgrades. It had a LEED Silver rating requirement at the time of the project. So specific window requirements that we determined early on in sitting down with the owners. They wanted this to meet the Secretary of Interior standards, National Landmark, but because it's a government building, they wanted the window project to meet blast resistance. They had energy performance requirements, sustainability requirements, and maintenance requirements. Now the existing windows that we had to deal with were formed steel sheet metal, double hung windows, single glazing. There were about 1,200 windows on the project, and the windows were not in great condition. They hadn't been painted or cared for about 25 years, and there was a lot of deterioration. So this next slide is just showing you what some of those existing conditions look like. Paint had failed. You had significant corrosion in areas. Some of it caused warping that prevented the windows from closing tightly, so you had air leakage through the windows. There was a lot of deterioration, rust jacking. So in combination with the architect, we came up with two scenarios that we wanted to do mock-ups of. One was to restore the existing windows and add an interior blast-resistant storm. This would allow us to improve the energy performance requirements, but also meet the blast requirement. As part of this, we were reusing the existing glass, changing out perimeter sealants. We were making them fixed windows, not operable windows anymore, because the operability was not required with the interior storm. And we were providing an interior blast-resistant storm that had laminated glazing and then also had low E coatings to help with its energy performance. And they selected low iron glass to allow it to have better visual transmittance through, and also just to reduce the greening effect of the glass. The other mock-up that they were considering was new blast-resistant thermally broken aluminum windows. So they were planning on replacing out the existing windows and putting in a new contemporary window in its place. So what we did is do two mock-ups, one of each, and then did a bunch of testing on it to verify the performance of those two windows, specifically focusing on the air infiltration and thermal monitoring to see whether you would be getting energy improvements and which window performed better. So some pictures of the two mock-ups in progress. This is the restoration mock-up. So you can see the existing jamb and counterweight pocket, the steel removed. You can see in the right-hand photo a steel Dutchman being put in place to deal with areas of significant corrosion. These are the windows after they've been cleaned and painted. And then you're looking at, they're starting to install an interior storm window which was attached to the existing frame as part of this. Then some photos of the replacement mock-up. Because they didn't know which way they wanted to go after these mock-ups were done, we carefully removed the existing window and salvaged it in case that they decided they didn't want to go with a replacement solution and might want to put this existing window back in place. Once they did this, they had to make repairs to the plaster and interior finishes around the window. This you can see that the new window is installed with its glass clips anchored to the surrounding masonry. These are pictures showing the replacement window in place, some of the plaster repairs in place, and its final installation looking from the interior. So looking from the exterior, this is a picture showing the two windows side by side. The window on your left-hand side is the replacement window. On the right-hand side of the photo is the original windows. Ironically, and maybe surprisingly, the restoration actually cost less money than the replacement did, even putting in the interior storms. Just to give you an up-close view of what the side-by-side looks like, these are just some piecemeal shots comparing the two windows. So your right-hand side head and sill details of the original window with the new storm on the inside, and then the left-hand side is the replacement window. The replacement window sight lines are similar to the existing window, but not exact. This was not a custom replicated window. It was a more off-the-shelf arrangement. So obviously, from a historic fabric perspective, there was some benefits to being able to keep the windows, but how did they perform energy against the other criteria that were being considered? So we did air infiltration testing to first answer that. And what might be surprising to everyone is the refurbished window with the storm performed about 50% better in terms of air leakage than the replacement window. We think this is because the painting over all the conditions really sealed up all the joints in the system, whereas a modern extruded section had individual components that were more likely to have air leakage. You had operable windows in the replacement versus fixed, and that was probably some of it too. Both windows performed to meet modern air leakage standards, however, so they were both high-performing windows, but the restored performed better. We then wanted to tackle how they performed thermally, and we had a couple of different options to get the best data. One was to do some steady-state calculations, but this didn't really predict its dynamic performance, and we didn't think would accurately capture what we were going for. We could do computer simulations, or we could look at a mock-up installation. We chose to do the monitoring process. It was a pretty complicated process. We had thermocouples and data loggers, and we actually set up some enclosed chambers and monitored it for 12 weeks in an enclosed chamber and 6 weeks then once the chamber was removed to try to look at the temperature and energy performance data throughout this. What we found is that, again, generally speaking, the repaired window performed better. It experienced less heat loss through the window. It had some more heat gain, and that had to do with the placement of where the low E coating fell on what painted glass, and we felt that that could be improved over time. But generally, because steel is less conductive than aluminum, and where the storm was placed, the repaired window performed better. So this chart is very small and hard to read all of this. You can come back and take the slides. In general, though, the conclusion was that the restored window was better. It performed better thermally. Neither window really had potential condensation. The restored window was easier to construct because it didn't get into interior finishes. The restored window was more sustainable because we were reusing existing materials. Maintenance-wise, the restored window was going to require a bit more frequent maintenance with painting, but the components themselves had a long-term durability, whereas the replacement window with insulating glass units typically an IGU only lasts about 25 years before the hermetic seal fails and you get condensation within, and the restored window costs less. So obviously I think you can understand where the conclusion is. They decided to restore the windows and not replace them in this case. So the last couple of case studies looking at the walls themselves to conclude. Insulating mass masonry buildings. If you wanted to look at adding insulation on the interior on these sorts of systems, you have to consider that you're going to lose historic fabric to expose the walls. If you're in a freeze-thaw climate, not so much of a problem in California, you have to consider whether the masonry itself is durable. If you see the picture on the bottom, that's 5 different bricks, and they're labeled with different compressive strengths, ranging from 610 to almost 11,000. Obviously, not all bricks are made the same. Some are more durable than others. You have to understand that if you're going to insulate on the interior, because these walls typically dry to both the interior and exterior, that's going to change how the wall performs. You might get the potential for condensation within the wall system as a result of increased moisture, or you might have to deal with corrosion. So these are all factors that need to be considered. Quickly commenting on the loss of historic fabric, this is a project we were involved in. Picture on the left is the before conditions, picture on the right is the after. All of the shaded areas you see here are all interior finishes that were removed in order to accomplish this project. So, depending on what you consider historic, there was a lot of historic material that was lost here. Just to highlight the idea of brick deterioration in a freeze-thaw climate, which I know you really have less of, it is a real consequence. This is a project that was insulated in the 1970s with foil-faced insulation that you couldn't get breathability through to the interior. Areas where you had high water leakage, so below cornices and gutters, we saw a real deterioration of the brick behind where it was getting significant water in the wall system. So the case study that we looked at was taking down interior structural clay tile with plaster and putting up closed cell foam with steel studs on the inside. To determine if this was suitable, you have to first test the brick masonry for its properties, just because all brick are not made the same, and the properties that go into the hydrothermal modeling really are variable to the bricks themselves. So this is a step that has to occur. On ours, we used a program called WOOFY that looks at the vapor drive, water content, and temperature through the wall system. And using that analysis with calibrated properties for the brick, we were able to determine that the exterior brick was so dense that there wasn't a lot of water absorption into the wall system. So with proper flashings and other roofing considerations, we didn't expect a lot of brick in the wall system, and it was appropriate to be able to insulate. This is just showing what that looks like, where they took off all of the interior finishes, put up closed cell spray foam, where we didn't have to worry about vapor permeability to the wall system, or where we had below grade walls and we were a little more concerned that you might get water into the wall system just because they were buried below grade. We put open cell spray foam with a smart vapor retarder. The smart vapor retarder just allows you to have some vapor throw. It's a one-directional vapor flow through, so that vapor from the wall to the interior can flow, but not from the interior into the wall. This same sort of approach would be appropriate for modernist concrete buildings. Luckily with these, you have less worry about freeze-thaw durability of the concrete itself, and so you don't have to do some of the modeling and testing. That's what you have to do with brick masonry. My last 2 examples, unfortunately, were not actually put into construction. They're ones where we did some peer review and consulting with architects. The first is a 1960s precast concrete storefront window system, with a spandrel panel. This might not normally be considered historic, but in Vermont, where it's located, it was. It's one of the first buildings of this type and is actually listed on the state register. And as part of this, they were changing it into laboratory space with humidified spaces and really worried about the performance of the wall system. So they asked us to look at it. Existing single pane windows, not thermally broken, aluminum windows, precast concrete panels, and discontinuous insulation that was isolated. So it was not a very good performing window, and when we were increasing the humidity on the inside, there were concerns about condensation. So we did some consulting with the architect who was in charge of the project just to look at what options there might be. The first one we considered is putting an interior storm setback with new interior walls, trying to connect air barriers between these new windows, the existing windows, and the new wall systems to get a continuous air and vapor barrier within the wall system. So that's looking at the sill. This is looking at the head. The blue is the insulation, the red is the window system, and the green is air barrier connections with membranes in between to try to achieve this, but still leave the historic materials in place. The second option they looked at was just doing retrofits to try to improve the wall panels, but to not try to put replacement windows in. So it was just creating air seals where we could with spray foam and with membranes similar at the top and bottom, and tying them into the existing windows. Our modeling, those show that we still have potential concerns with condensation on the curtain walls with the humidified space. And then the last option they considered was actually getting rid of the historic storefronts and putting in a new curtain wall system for that. So that's just the head and sill details for those. Unfortunately, we didn't go so far as to do energy modeling and real comparisons on performance on these because they were just looking at mock-ups, and then funding went away and they didn't actually install any of this. But it gives you some idea of what you might do on the inside for systems of this type. The last is just a little bit more of a creative brainstorm we did with an architect at one time. This is a water facility, pumping station that had been left into disrepair. And this architect, it was near a college campus, and they were thinking, you know, somebody could take this and revitalize this building to be a modern conference center. And they were trying to brainstorm ways to do that. A mass masonry building that had obvious need for repair beyond just energy improvements. But the added wrinkle is the interior of this space is just incredible when you consider what an industrial space it was, with the polychromatic brick, the interesting steel roof structures, and they wanted to capture all this. So brainstorming a little bit outside of the box, we actually proposed on this one to do a box in a box, to put a glass box within inside so that you could get more modern performance standards, you can control your interior air, better control your energy usage within the building, but still be able to see and appreciate this historic building. So this is sort of just giving you an idea of what the space usage within this would be. Again, it didn't progress beyond sort of creative reimagining of what this building could become, but it gives you an idea of what might be a creative way on a historic building to make it more modern performance and energy performance. So with that, that is my last example. Hopefully everyone is still awake, and if anyone has any questions.
Thank you, Susan. While we're waiting for questions, I'll pick up a few here, and anybody that's currently logged in, if you'd like to ask a question and you're dialed in, you would press *6 on your phone, or you would type your question into the chat box or the Q&A box. The first question I'd like to ask, Susan, is what about certain I guess it would be unique challenges with windows, things like bay windows or projecting windows, and how do you best create a barrier in those kinds of situations?
So I'm not quite sure exactly what you mean by that, but a lot of bay windows, bow windows are still just ganged window systems, and so you're looking to make sure you connect the individual frames within that to have an air seal between the frames, and then to get seals around the perimeter of those.
Okay, yeah, I think that somewhat answers the question. And you briefly mentioned the embedded energy and considering that in any sort of project scope. But is there an easy way, or have you found an easy way to calculate the embedded or the stored energy of buildings and use that sort of information to advocate for the existing structure instead of replacement?
So we haven't gotten into a lot ourselves where clients have asked us to quantify that. I know that there's been some national trust studies that have taken that into consideration, and I can look up for someone the reference to that study where they've tried to look at improved performance versus what the replacement value of a building is, and look at some of the life cycle costs and other issues. So there's some articles out there. Most of our clients have not asked us to quantify that as much. It's sort of just a qualitative knowing that where you can, it's better to reuse versus replace.
And a third question about the Lafayette building, and I think it was about why the replacements ended up costing less than, or, I'm sorry, not the replacements, the existing windows ended up costing less than the replacements.
So a lot of it had to do with the fact that the replacements got into interior finish repairs, and so you had to remove plaster and reinstall plaster, and it's different trades getting involved. Is what really increased some of the cost to that.
Okay. Fourth question is, could you briefly describe how you handled HVAC in some of your case studies?
So we're typically partnered with other firms in terms of the HVAC. We're looking at, most of these, like the Lafayette building, we were under an architect who had hired a different HVAC designer. We're typically on that, helping to feed them performance characteristics of the envelope so that they can better size their system for performance. But the decision had already been made on those, in terms of replacement of the system. When we get asked earlier in the process and are creating the actual energy model, we're looking as part of our studies at upgrading equipment and what the cost of that upgrade would be.
And more out of curiosity, whatever happened with the water treatment plant?
Right now, it's still sitting unused. I think the architect who had taken a love for that building still periodically pitches it to the local university to try to get it in their master plan that they should take ownership of this building and revitalize it, but nothing's been done yet.
Okay, so I think that's, if there are no further questions, I don't see any more rolling in. I'll give people about 10 seconds here to ask any final questions, but we are coming up on our time anyways, and I wanted to thank everybody for supporting the California Preservation Foundation, and also thank Susan for her time and wonderful presentation. You're now looking at the evaluation page. This allows us to receive feedback from you on this session, but also our education programs in general. What you would need to do is respond to each of these questions, multiple response sort of survey responses, and then scroll up to the top of the page and hit the submit response button. At the top of the page in the center is a related links box where you can visit more information about this session, but also about our upcoming programs. This is the final program of 2014, 2013/2014, but also we will be posting the 2014-2015 schedule by mid to late October. So keep an eye out for any programs at news.californiapreservation.org/events. Those will be appearing soon. And please also type in your responses, written responses, if you have any suggestions for future topics, and if you'd like to provide any additional comments on today's session. Again, thank you, Susan, and I hope everybody has a wonderful rest of the day. And feel free to contact us if you have any questions or queries, or if you'd like to get in touch with the speaker. Have a great day. Bye.